Bismillahirrahmanirrahim. So today we would be discussing damped free vibration. Up till now we were actually discussing undamped free vibration, in which we were not considering the damping in the system, that is the energy losses. And that modeling is true in all those cases where the energy losses are small, and we could ignore the energy losses or the damping in the other case. In those cases, because the damping is less, so if we ignore the damping, then what would happen? The modeling would become very easy. Similarly, in order to develop the equation of motion for the system, that would become very easy. And also very easily we would get the solution of that differential equation, or the response for that differential equation, or the response of the vibration. So actually we are doing that in all those vibratory systems where we before in hand we know that the damping in the system is less, it is ignorable, and by doing so it would have very less effect on the accuracy of the modeling and accuracy of the answer of the computation. But actually in the majority of the cases during the vibration or in the vibratory systems, the energy losses, that the energy which is going out of the vibratory system, that is considerable. And in all those cases, we have to consider the energy losses, which we are terming as the damping in the vibratory system. So there are a number of damping in the vibratory system. For example, we have air damping, or it is also known as fluid damping or viscous damping. And that damping is actually present in the system because of the air or the fluid around the moving parts in the vibratory system. As there is air or fluid around the moving part of the vibratory system, so as it moves, so it displaces the molecules of the air and the fluid. In turn, doing that, actually what happens, because we are giving motion, the system is giving motion to the molecules, so it takes actually the energy in the form of the motion, and in such a way the energy is imparted to the fluid or the air molecules which are around the moving parts of the vibratory system. Energy is going out. It means that the energy is going out or dissipated in the system. It dissipated from the system and into the fluid around the moving part of the system. So that energy loss is classified as the fluid damping. The other type of damping is known as Coulomb damping. And this Coulomb damping actually is because of the dry friction. When there are two moving parts and they move relative to each other, which normally happens in some, actually in vibratory system, two surfaces are moving relative to each other. So what happens, there exists friction, and because of that dry friction heat is generated, which is the energy. And we know that energy can neither be created or not destroyed. That energy would be coming from somewhere. And in this case, that energy is coming from the vibratory system. So the energy would be taken out from the system. So we have to model it as a damping. And in this case, we call or classify that as Coulomb damping. The other type of energy loss or damping that occurs in the system is classified as the material damping, and this happens inside the material of the system, because as the material is vibrating, as the system is vibrating, the material is deforming, So when it deforms, so what happens? The inter layer of the material, they move relative to each other, and whenever there is a relative motion between the inter layers of the materials which are adjacent to each other, whenever there is friction, there would be heat generation, and that heat, which is again energy, it would be coming from somewhere, and in that case, in this case also, that energy would be coming from the vibratory system, and we would term this energy loss as the material damping. And the fourth type of energy loss, which normally happens in the vibratory system, is actually happening through the support. Because the system is vibrating, it would have a frame or support which is actually necessary in order to keep up the system. And actually, during the vibration, some of the energy actually transfer through the support, and it is going out from the system, and that energy which is going through the support or through the frame of the system is classified as the support damping. So we would have actually generally we would have viscous fluid damping, Coulomb damping, material damping, and support damping inside the vibratory system. And whenever the damping, this damping is considerable, and then we have to consider it, and we have to model our system as damped system. And next, actually, what we would be discussing is the damped free vibration. So now, from now on, we would include the damping in the system or energy losses in the system. It is actually remember that it is important to know that sometimes one type of the damping would be dominant, whereas the other damping would be actually less. So it depends upon the type of the system and the type of the fluid in which it is working. For example, it is possible, and it is actually normally sometimes happens, that the system, vibratory system, normally vibrates inside the vacuum. So in that case, as there is no air or fluid around the moving part of the system, so in that case, actually, there would be no fluid damping. If there are no mating parts in the vibratory system, then there would be no Coulomb damping. In that case, only there would be two dampings which would be dominant, that would be the material damping and support damping. The material damping also depends upon the nature of the material. In some materials, the material damping is too much. However, in some materials, the material damping would be very, very small. And it would be so small that we could ignore. So remember that it is not necessary that in a vibratory system, all these four types of damping types would exist. Sometimes some would be dominant and the other would be so less that we could it could be ignorable. So viscous damping or the fluid damping, in that case, damping force is proportional to the velocity of the vibrating body in a fluid medium such as air, water, gas, and oil. So in order to model the viscous damping or the fluid damping or air damping, it is modeled such that the damping force, that is F subscript D, it is directly proportional to the velocity of the mass. So if the mass is vibrating at high velocity, then the damping force would be more. If it is moving with low velocity, then the damping force would be less, or the energy dissipation would be less. So removing this sign of proportionality, that is, we try to convert that into equality sign. For that, we have to include the proportionality constant, and in that case, the proportionality constant is C, which is actually the coefficient of damping or damping coefficient. So the equation that we would be using in this course, it would be Fd, the damping force, and it is equal to C x dot, where x dot is the velocity of the mass and c is the damping coefficient. And this actually damping, we call it linear damping. The damping force is directly proportional to velocity, so this is classified as linear damping. And the damper that we would be the damping that we would be modeling, that is called the linear damper. In Coulomb or dry friction damping, the damping force is constant in magnitude but opposite in direction to that of the motion of the vibrating body between dry surfaces. So as you have studied the friction, so in that case, if this is the applied force or the vibratory force, so the damping force is always opposite to the motion of the mass, and it is actually equal to mu times n, where n is the normal force. And this damping force is opposite to the applied force or opposite to the motion, and also it is constant in magnitude. It is not directly proportional to the velocity of the moving mass. So the damping force in this case would be modeled as Fd is equal to mu n, where n is the normal reaction and mu is the friction coefficient. Material or solid or static damping. Energy is absorbed. Energy is absorbed or dissipated by material during deformation due to friction between internal planes. As we discussed before, as when during vibration, the material moves and it deforms. So the internal planes which are adjacent to each other, they move relative to each other. And whenever they move relative to each other, so what happens, there is friction between them, and because of this friction energy is generated, and that energy would be actually coming from somewhere, because energy can neither be created nor destroyed. So in this case that energy would be coming from the vibratory system, and actually we would call this type of damping or energy loss as the material or solid or static damping. So actually, in real systems, in real vibratory system, there is energy dissipation or energy losses. So during modeling, we have to consider those energy losses if they are actually not ignorable. So in this course, we have to model them as linear viscous damper or linear viscous damping. And this is actually the schematic that we would be using in the lumped parameter modeling. It is also known as dash put or viscous damper or simply damper, and it is somewhat like a shock absorber. So it is a, this represents a cylinder and this represents a piston. So it has two ends. This is one end and this is the other end. In this case, one end of the damper is fixed, whereas the other is free and it is actually moving with some velocity. And as we discussed that in case of viscous or fluid or air damping, the damping force is directly proportional to the velocity. So Fc is equal to C x dot of t. X dot of t is actually the velocity at which the mass is moving or vibrating, and C is actually the coefficient of damping or damping coefficient. It is also it is the constant. It is also called the damper constant, and its unit is Newton second per meter or kilogram per second. And if we want to find out C from this equation, so the damping C is actually equal to the damping force divided by the velocity. So that's this is actually the lump parameter model for a real system. This is a lumped parameter model. All of the mass we are taking here in this block, and all of the elasticity we are taking in this spring, and all of the energy losses we are taking in this damper. So this sort of modeling is known as lumped parameter modeling. So this is the simplest modeling that we could do for the um, dynamic systems. And in this is a linear vibration course. So in this we would consider that the spring stiffness is linear, the damper response is linear, yeah, and also, for example, the mass, it is not changing during the vibration. And so we have a mass, it is supported by this spring and this damper, and let's say at this instant the mass is moving in the downward direction, and this is the fixed support. So this is actually the lump parameter model of a real system. So in order to first, as we discussed last time, that the first step that in order to have solve the problems in the vibration, you have to derive the equation of motion. And for the equation of motion, you have to first draw the free body diagram. So let's say the mass is moving in the downward direction. So in that case, the damping force, remember that the damping force is always opposite to the motion. If the mass is moving in the downward direction, the damping force would be in the upward direction. If the mass is moving in the upward direction, the damping force would be in the downward direction. It would be always opposite to the motion because it is the damping force, because it is representing the energy losses, and only the losses would happen only in that case if the force, the damping force, is opposite to the motion. Let's say if we consider the weight which is acting in the downward direction, and this weight would be balanced by the static deflection force which we discussed in last lecture, and that static deflection force is k delta. So these two are equal, we already discussed. So they, in the equation of motion, they would cancel each other. Here I'm showing you that these are included in the modeling, but when we would write down the equation of motion, they would cancel each other. So all the time we would be not writing these two, k delta and mg, because it is understood that they are present there, but they would, at the end, when we put in the equation of motion, they would cancel each other because they are equal in magnitude and opposite in direction. So they are there, but as they would cancel, so all the time we would be not writing them in the equation of motion. And as the spring moves through a distance x in this direction, so the spring would extend and it would actually pull the mass in the upward direction. The spring force would be in the upward direction, and because of x, its magnitude would be kx. So this is actually the free body diagram for this system, spring mass damper system. Now using the Newton's second law, that is the summation of all of the algebraic forces which is acting on the mass, it is actually equal to mass times acceleration, and we have to take all those forces which are along the displacement as positive. So mg we have to take positive, and all those forces which are opposite to the displacement as negative, so minus kx plus k delta minus cx dot is equal to mx double dot. And so these two would cancel out because they are equal in magnitude with opposite sign. So at the end, if we rearrange the equation of motion would be mx double dot plus kx dot plus kx is equal to 0. So for this spring mass damper system, we got the equation mx double dot plus cx dot plus kx is equal to 0. So we have a spring mass damper system and it is subjected to free vibration. Remember that we have subjected the system to the free vibration. It is actually disturbed once, and as it start vibration, during the vibration the disturbance is not present and it is actually vibrating by its own in the absence of the external force or the force of excitation. So on this side we have 0. In case of normally you would see that in case of force vibration there would be a forcing function there, but in case of free vibration there would be no forcing function, 0 forcing function, so we would have 0 here. So if we look at the differential equation, we have second order differential equation. You see two dots here, so we have second order differential equation, homogeneous differential equation, because on this side we have 0. We have a linear differential equation. If you look at here, the variable is x. It has power 1. X dot has power 1. The x double dot has power 1. So we have a linear differential equation. Constant coefficients k, c, and m, they are constants. They are not changing during the vibration. So they are constant. So we have a second order differential homogeneous equation with linear and constant coefficients. So linear second order homogeneous differential equation with constant coefficient. The solution of this equation, the solution is actually the response of the system, and the response of the system x of t could be modeled as x sine omega t plus phi, where x is the amplitude and omega is the frequency and phi is the phase. Similarly, in complex plane, we could write the equation for the response as x of t is equal to c exponential st. So viscous damped free vibration. So we got the equation of motion mx double dot plus cx dot plus kx is equal to 0. Now we would play with the equation. So I'm dividing the equation throughout by m in order to write the equation in terms of natural frequency and damping ratio. So if we divide it by m, so here we would have 1, and here we would have c by m, and here we would have k by m, and k by m is actually omega n square. Here we got c by m. So omega n is actually under the root k by m, and here we would define another parameter, which is actually the critical damping. Critical damping, we would discuss this critical damping in the coming lectures, but up till now, remember that critical damping is the property of the system. And this is actually the damping which is bringing the system to the equilibrium position in the least time. In the least time, if we have critical damping, then this damping would bring the mass or the system to the equilibrium position in least time. So we would have further discussion in the coming lectures, and that critical damping is modeled as Cc. It is denoted by Cc, and it is modeled as 2m omega n. So it is actually the property of somewhat the property of the system, because you could see that it has mass and omega n, which is the natural frequency. If we put for the omega n, which is under the root k by m, then we could rewrite this equation as 2 under the root km. So this is actually the mathematical model for the critical damping. We also defined zeta, Zeta is the damping ratio, and it is the ratio of the damping in the system to the critical damping. And for the critical damping, we have this model. And damping, the actual damping in the system, let's say it is C. So the damping ratio would be C divided by Cc. So zeta is the damping ratio, and it is unitless because it is the ratio of the damping. Zeta, if we put the equation for the Cc, so zeta would be equal to C divided by 2 under the root Kn. And it is known as damping ratio. It is dimensionless. It has no unit. So here, once we divide the whole equation by m, so we would have C by m. We would have C by m. So if we divide C by m, if I bring this quantity here, then we would have C is equal to zeta Cc. And if then I divide the equation by m on both sides, so we would have C by m, whereas on the other side we would have zeta Cc by m. And zeta and Cc, we have 2m omega n. And if it is divided by m, then we would have C by m is equal to 2 zeta omega n. So let's say I will write those here. I will write this derivation here. So from this equation, we could write down that C is equal to Cc times zeta. And if I divide both sides by m, so here we have C by m, and here we would have Cc zeta by m. And if I put for Cc as 2m omega n, we have this zeta here. So this zeta divided by m. So this m would cancel out this m. So C by m would be equal to 2 omega n times zeta. So here you see that once we divide, the equation by m, we would have C by m, and that C by m is actually 2 zeta omega n. So now we have the equation in the standard form, that is in terms of natural frequency omega n, and in terms of the damping ratio. You see the damping ratio here, and you see actually the natural frequency. So remember that once we have the equation of motion for the system, and we divide the whole equation, whatever we have a coefficient here, then the quantity that you get here, that quantity would be 2 zeta omega n, and the quantity that you have here, that would be omega n square. So from the quantity there, we could find the omega n, the undamped circular natural frequency, and here we could find out zeta, the damping ratio for the system. And from that damping ratio, we could find out the damping, because Cc, once we have omega n, we have mass for the system, so we could find Cc. So once we have zeta, very easily we could find out the actual damping inside the system. So next we would, now we have the equation of motion for the damped system, when it is subjected to free vibration, next step is to find the response of the system. That how would be the response of the system? So we are assuming that the system is vibrating and the vibration is sinusoidal. It is periodic. So in that case, we could assume the response as x of t is equal to a exponential lambda t. So we are treating the problem as eigenvalue problem, or we are using the eigenvalue method in order to find out the roots of the equation, roots of the differential equation. So once we are using this as a solution of the differential equation, so it means that this solution must have to satisfy the equation of motion. So what we have to do, if you look at the differential equation, here we have x double dot, here we have x dot, here we have x, and we are assuming the solution as x is equal to lambda, x is equal to a exponential lambda t. So here with the omega n square, we have x, so a exponential lambda t. Here with 2 zeta omega n, we have x dot, so we have to differentiate this once with respect to time. So differentiating this, we would have x dot of t, and it would have a exponential lambda t, and when it is differentiated, the power is of exponential function is differentiated, so we would have lambda from there. So we would have lambda a exponential lambda t. And for x double dot, again we have to differentiate this again. So a is constant, so it would be here, and then the differential of exponential lambda t is again exponential lambda t, and when it is differentiated, the power of exponential function is differentiated, again we would get one more lambda. So at the end we would have lambda square a exponential lambda t. So here, as we discussed before, we could take out lambda a, we could take a exponential lambda t common. So inside the parentheses, we would have lambda square plus 2 zeta omega n lambda plus omega n square is equal to 0. So it means that either exponential lambda t is equal to 0, or whatever we have inside the parentheses, that is equal to 0. That's why the product of the two quantities are 0. But we know that a exponential lambda t is actually the displacement, and all the time during the vibration, this displacement cannot be equal to 0. Otherwise, there would be no vibration. If we take this as equal to 0 all the time during the vibration, so it means that no vibration is happening. But that is not the case. We are assuming that the vibration, we have a vibratory system, the system is vibrating, and x, there would be x of t. We know that at the mean position x of t is 0, but at all other instances we have displacement. So during all of the vibration, during all of the time, actually that quantity is not equal to 0. It means that anything which is inside the parenthesis, that is lambda square plus 2 zeta omega n lambda plus omega n square, it must be equal to 0. And this is actually known as the characteristic equation. This is actually the characteristic equation of the system. So with the eigenvalue method, what we have done, we have converted a differential equation into an algebraic equation. So now it is very easy to find out the roots of a algebraic equation. It is a quadratic equation, so we have to just use the quadratic formula, which is minus b plus minus under the root 4 b square minus 4ac whole divided by 2a. So you have to just use that quadratic equation. So using the quadratic equation, we would have two roots for this equation, lambda 1 and lambda 2, and it would be equal to minus zeta omega n plus minus omega n under the root zeta square minus 1. Here a is 1, a is 1, this is b, and this is c. So using that quadratic formula, you could find out the roots of the characteristic equation. So we have two roots, one with the positive sign and one with the negative sign. The nature of this root actually depends upon the value of this discriminant. Actually, anything which is inside this square, it is known as discriminant. So the nature of the root actually depends upon the value of this discriminant. So here the discriminant, that is zeta square minus 1, determines the nature of the roots lambda. Now for the nature of the roots, we have three possibilities. The first possibility, so depending upon the value of zeta, there are three possibilities. So the first possibility is that when zeta is equal to 1. And when this would happen in the system when the actual damping in the system is equal to the critical damping. As we discussed that the damping ratio zeta, it is C by Cc. So if the actual damping is equal to the critical damping, then in that case the damping ratio would be 1. And when the damping ratio is 1, if you look at this equation, if zeta is 1, so the square of 1 is 1, so 1 minus 1 is 0. So this quantity would become 0. And in that case, we would have lambda 1. Lambda 1 would be equal to minus zeta omega n, and also lambda 2 would be equal to minus zeta omega n. So it means that we would have equal and repeated roots. We would have equal and repeated roots. So lambda 1 is equal to lambda 2, as zeta is actually 1. So zeta vanishes from the equation because by putting is equal to 1. So we would have lambda 1, lambda 2 is equal to minus omega n. So we have equal and repeated roots. And in mathematics, we have studied that if we have equal and repeated roots, then the solution of the differential equation would be x of t is equal to a1 exponential lambda 1 t plus a2 time t exponential lambda 2t. So this would be actually the solution of the differential equation. So plugging for lambda 1 and lambda 2 in the equation, the response x of t would be a1 exponential minus omega nt plus a2 t exponential minus omega nt, where a1 and a2, they are arbitrary constants. And in order to find out actually these arbitrary constants, we have to use the initial conditions. And last time we discussed the initial conditions, that is when time is equal to 0, what is the displacement? When time is equal to 0, what is the velocity? So x of 0 is equal to x naught, and x dot of 0 is equal to v naught. If x of 0 is equal to x naught and x dot of 0 is equal to v naught, if we use that initial conditions and we use here in this equation, then we would get the arbitrary constants, that is a1 and a2. So if you use the first initial condition, if we put this 0 here, t is equal to 0 here, so what would happen? This term would become 0. And at the end we would have a1 exponential, this is 0. So this whole term would become 0. Exponential of 0 is 1. So here we would have a1. X of 0 is, let's say, x naught, then x naught would be equal to a1. In other words, a1 is equal to x naught. And in order to use the second initial condition, which is x dot of 0 is equal to v naught, first you have to differentiate this equation with respect to time so that we get x dot of t. So once we have x dot of t, Once we have x dot of t, then you have to put 0 in that. So x dot of 0 is v naught, and we have to put a1 as x naught, and the only unknown in the equation then would be a2, and from there you would find out a2 is equal to v naught plus omega n x naught. So meaning that just by utilizing the initial conditions, we could find out these arbitrary constants a1 and a2. So after putting these arbitrary constants here in this equation, a1 is x naught and a2 is v naught omega and x naught. We are putting that here. The equation for the response would be x of t is equal to x naught plus v naught plus omega and x naught times t, and then out of the bracket we have exponential minus omega and t. So if we look at the response equation, so very easily we could see that the response would be not a vibratory response. It means that no vibration is actually happening in this case. If you disturb the system would not vibrate, because in the response, if you see, we are not seeing the sine function, we are not seeing the cos function, we are not seeing exponential iota function. Here we have an exponential function, but if you look here in the power, there is no iota. There is no iota. If you remember that exponential iota theta is actually cos theta minus sine theta. So exponential iota theta function is actually a sine and cos function. So if we have that function here, then it would mean that the response would be a vibratory response, a sinusoidal response. But we are not seeing, there is no iota here. This is an exponential decaying function. Exponential decaying function. It is actually reducing whatever we have here. It is decreasing that, and it is decreasing this exponentially with respect to time. It means that as the time increases, it would eat this quantity, the quantity on its left side as the time increases. So while you first we look at here that we have an exponential decaying function. So it means that this exponential decay function would eat whatever we have here with the passage of time. And also if we look here, this is a constant, x naught is a constant, v naught is a constant, omega n is the natural frequency of the system for that particular system, that is constant. X naught again appears, that is constant. Time, it is changing, it is increasing, t is increasing with time. So meaning that this quantity would increase with time, but here this quantity would drag it down, and it would eat, after some time it will eat all this quantity. So just looking at the equation for the response, this mathematical model actually tells us that there would be no vibration, so no oscillation occurs. And actually we would have normally in our real life, we have this actually mechanism, this critical damping. It is known, and when zeta is equal to 1, we call this critical damping or critically damped system. We call the system as critically damped system. And actually in practically in some cases our systems are critically damped. For example, the door closing mechanism, which we have, the hydraulic door closing mechanism, which we have in the door. In that, actually, we keep the damping as critical, because we want that when the door is opened, then actually the hydraulic mechanism would shut down the door, and it would shut down the door slowly and gradually in the minimum possible time. So we would have damping in that hydraulic mechanism of the door, and we would keep the damping as critical. As I told you before, that the critical damping would bring the system, once it is displaced from the equilibrium position, it would bring the system back to the equilibrium position in the shortest time. So we have to keep the damping in that system as critical. And also in analog devices or analog gauges, for example, analog pressure gauges, analog ammeter, voltmeter, wattmeter. By analog, we mean those devices in which we have needle. So once that device is subjected to um, actually to transient uh, input, so what happens? The needle actually moves suddenly. It moves suddenly. For the needle, we have actually a mechanism. We have a damping mechanism. There is a cylinder and there is a plunger. There is a damping mechanism inside that. And in that damping mechanism, the damping that is kept is critical because we want that the needle moves, but when it becomes stationary, it should not vibrate at that position for longer time, but it should move and it would get stationary at the reading place so that we take the reading quickly. If it is vibrating too much at the reading place, if the damping in the analog gauges is less than the critical, then the needle would vibrate. And if there is no damping in the device, then the needle would vibrate for all time. And it is very difficult to take the readings. So normally to take the readings quickly and accurately, normally in all analog gauges, the damping in the needle mechanism is kept critical. So here we could also see that the response of the system would actually depend upon the initial conditions x naught and v naught. So if we change the initial condition, the response would change. So we would try a few examples where we would be changing the initial conditions, and then we would see how the response of the system would be. Let's see if we have this initial condition. If x naught is equal to plus 0.4 millimeter and v naught, that is the initial velocity, is plus 1 mm per second. If you use this initial condition and if you simulate this equation in the software just like MATLAB or Excel, we would get this plot. We would get this plot. Along the vertical, we have the displacement, that is x of t, and along the horizontal, we have the time. So if we simulate this equation for this boundary condition, we would have this response. So in order to explain how the response would be this, because there would be no vibration, so it means that if we move the mass, if I displace the mass and then I give initial displacement and then I release the mass, then slowly and gradually the mass would come to equilibrium position. So let's say if we have this mass and a spring, I'm not showing the damper, but the damper is there. This is the mean or equilibrium position. We have two extreme positions. So this is the top extreme position, this is the bottom extreme position, and between these two extreme positions, the mass is there. Now look at the first response. That is x naught is equal to 0.4 mm and v naught is equal to plus um, 1 millimeter per second. And let's say the mass is moving in that direction, we are taking this as positive. So it means that the x naught is 0.4 mm. What is the displacement at the mean position or equilibrium position? 0. So it means that the initial displacement, since it is 0.4 millimeter, so it means that the mass is not here. It is not at the equilibrium position. And if we look at the velocity, it is not 0. The velocity at the extreme positions are 0. So it means that the mass is also not reach the extreme position. The mass is here. It is at some intermediate position where the displacement is plus 0.4. So it is, let's say, some here. But since the velocity is not zero, so still it is moving. So it would reach the equilibrium position. And then since the system is damped system and we have critical damping, so from there the system would slowly and gradually, the mass would slowly and gradually come back to the equilibrium position. So we have a mass here and it is moving in the upward direction, so it would reach the equilibrium position. So here it has reached the equilibrium position, and from there it would slowly and gradually would come back to the equilibrium position. So this would be the response of the system in case of this initial condition. So you could assume that the system is just moving in the upward direction. It would reach the top extreme and then it would return back slowly and gradually to the equilibrium, but there would be no vibration. Now see the second initial condition. X naught is plus 4 millimeter, V naught is 0 millimeter per second. Velocity is 0. Displacement is not 0. Displacement is not 0, it means that it is not at the mean position. The velocity is 0, it means that the mass has reached the top extreme position. It is here. So the mass is here. At this initial condition, the mass is here. It just like that I'm holding the mass here at this equilibrium, at this extreme position. At this extreme position, the velocity is 0, and then if I release the mass would slowly and gradually come to its equilibrium position. So if you release the mass from there, the mass would slowly and gradually come to the equilibrium position. Now the third boundary condition, x naught is 0.4 millimeter and v naught is minus 1 mm per second. So the velocity is not 0, so it means that it is not at the extreme position. The displacement is not 0, it means that it is not at the equilibrium position. It is somewhere here, but it is moving in the downward direction. It is moving in the downward direction with a velocity. So it is at 0.4 and it is moving in the downward direction with a velocity. So it would reach the equilibrium position. What is the difference between the response during 2 and 3? If you look here the system is actually starting accelerating from 0 velocity, and here the system is actually starting the accelerating with velocity 1 meter per second. And the difference is that in this case the system is actually moving with a velocity 1 meter per second, so it would reach the equilibrium position quickly. So just by actually visualizing or idealizing, we could easily assume that in this case, in the third case, the system would reach the equilibrium position more quickly than the second case. So we have just seen that the response of the system in this case when zeta is equal to 1, it depends upon what? It depends upon the initial conditions. The response would be not oscillatory response. No vibration would take place. If you disturb the system, displace the system, or displace the mass would slowly and gradually come back to its equilibrium position. Second possibility, when the zeta is greater than 1, that is, and this would happen when C is greater than Cc, when the actual damping in the system is more than the critical damping, then zeta would be greater than 1, and this is called overdamping, and the system is known as overdamped system. And in that case, actually what would happen? Uh, since zeta is greater than 1, so the discriminant would be positive. Zeta is greater than 1, zeta square would be a positive quantity. Zeta square is actually greater than 1, so the square of that would be more than 1. So this discriminant would be a positive quantity. So if this discriminant is a positive quantity, then we would have lambda 1 and lambda 2, which are the roots of the characteristic equation. It would be minus zeta omega n plus minus omega n under the root zeta square minus 1. We have, in that case, we would have two distinct roots. Distinct mean different roots, one with the positive and one with the negative. And in this case, we would have real roots, and we would have also real roots. So we would have two distinct real roots. And if that is the case, then actually the solution of the differential equation would be x of t is equal to a1 exponential lambda 1t plus a2 exponential lambda 2t. So putting for lambda 1, that is once with the positive sign, and lambda 2, that is with the negative sign, after plugging that and taking exponential zeta omega nt common, then we would have a 1 exponential minus omega nt under the root zeta square minus 1 plus a2 exponential omega nt under the root zeta square minus 1, where a1 and a2 are arbitrary constants. And similarly, again, in order to find these arbitrary constants, we have to use the initial conditions, which are x of 0 is equal to x naught and x dot of 0 is equal to v naught. So once we use those initial conditions here in this response, so we would get a1 and we would get a2 once we would apply our second initial condition, that is x dot of 0 is equal to v naught. So after utilizing the initial conditions here, a1 would be equal to this quantity and a2 would be equal to this quantity. A1 is minus v naught plus minus zeta plus under root zeta square minus 1 omega n x naught divided by 2 omega n under the root zeta square minus 1, and similarly a2 would be equal to this quantity. In this case, since again if we look at the equation, just look at the equation, a1 is everything is constant here, x naught is constant, omega n is actually the natural frequency of the system, it is constant for that particular system, zeta is constant for that particular system, v naught is constant, so a1 is arbitrary constant, a2 is arbitrary constant. Again, if we look at the equation here, in order to see whether vibration would take place in this case or not, so you see no sine function in the equation, no cos function in the equation, no iota in the powers of the exponential function. So here you see that this is an exponential decaying function because we have negative sign here. Again, here we have an exponential decaying function. Here we have an exponential increasing function because there is a positive sign. So here we have an exponential increasing function, exponential decaying function, and these two are actually multiplying with the exponential decaying function. It means that as time passes out, this exponentially decaying function would eat whatever is inside the parenthesis. So as time increases, this quantity would increase, this quantity would decrease, it would eat this quantity, but at the same time, this exponential decaying function would eat all of this quantity. So it means that with the passage of time, when you disturb the system, the displacement would diminish and the system would come back to the equilibrium position. So just looking at the response of the system, we could very easily predict um, or analyze that there would be no vibration also in this case. So in case of our damped system, when the damping is more than the critical damping, there is overdamping in the system, then there would also be no vibration. Once you disturb the system would come back slowly and gradually to the equilibrium position. And again, we see that the response of the system depends upon what? Depends upon the initial conditions. The response of the system would depends upon the initial conditions. If you change the initial conditions, the response of the system would change. So let's simulate the response of the system for different initial conditions. So let's say our first initial condition is x naught is 0.3 and v naught is 0. V naught is 0, it means that the system is at the extreme position. The mass is at the extreme position. The mass is here. And from there, if we release the system, slowly and gradually the mass would come back to the mean position or equilibrium position. So this is actually happening in the first case. So initially the mass is at plus 0.3, it is here, and from there if we release the mass slowly and gradually, the mass would return back to the equilibrium position. Second boundary condition, x naught is 0 and v naught is plus 1. The mass x naught is 0, so the mass is here. The mass is at the equilibrium position. V naught is 1 plus 1, but it is moving. It is moving in this direction. If it is moving in this direction, it is just like that I have kicked the mass. It is moving with a velocity 1 meter per second or 1 millimeter per second, but it is still at the equilibrium position. So this mass would reach the extreme position, and from there it would return back to the mean position or equilibrium position. So for this initial condition, the mass is at the equilibrium position, so it is moving with a velocity plus 1, so it would reach the equilibrium position. It would reach the extreme position, and from there it would return back to the equilibrium position. Third boundary condition, x naught is minus 0.3 and v naught is 0. X naught is minus, so it means that the mass is at the other extreme position, it is here. And the velocity is 0, so it means that it is at this extreme position. So from here, if we release the mass slowly and gradually, the mass would return back to the equilibrium position. So it is at minus 0.3, and slowly and gradually, if we release the mass, it would reach back to the equilibrium position. So this would happen in case of overdamped system. So if we increase further damping in the system, it would take more time for the system to reach the equilibrium position. So as we are increasing the damping in the system, and it is more than critical, so as further you increase the damping in the system, the further it would take to reach the equilibrium position. And if there is too much damping in the system, so once it is disturbed, it would stay at that new position. If there is too much damping, then the mass would not return back to the equilibrium position. And once it is in the equilibrium position and there is too much damping in the system, so once we are applying too much force on the mass, it would be very difficult to move it. The third possibility, when zeta is less than 1. And this would happen because zeta is actually C by Cc. If C, that is the actual damping in the system, is less than the critical damping, so in that case zeta would be less than 1, and we call that damping underdamping, and that system as underdamped system. So if zeta is less than 1, the system is actually underdamped system, the motion is underdamped motion, and actually this is the most common motion in all of the vibratory system. In all of the vibratory system, the systems which are actually vibrating under free vibration, remember that under free vibration, If we disturb the system and that system vibrates for some times, it means that zeta is less than 1. The damping ratio is less than 1 for that system. It means that the actual damping in that system is less than the critical damping. So in this case, actually, if we look at the roots, if zeta is less than 1, and if we take the square of that quantity which is less than 1, it would further decrease. So meaning that in this case, the discriminant would be negative. Discriminant would be a negative quantity. So if the discriminant is a negative quantity, so actually here we would have minus 1. If I take common, minus 1 common, then that discriminant would become 1 minus zeta square. It would become 1 minus zeta square, and here we would have minus 1. And minus 1 under the root is j or iota. So I'm writing that j or iota here. So in that case, lambda 1 and lambda 2 would be minus zeta omega n plus minus omega n j under the root 1 minus zeta square. So since there is iota or j here, so meaning that we would have complex roots. We would have two complex roots, and we would have conjugate pair, one with the positive sign and other with the negative sign. So here in this case, we would have two complex roots as conjugate pairs. Since we have two complex roots with conjugate pair, so the response, that is the solution of that differential equation, the general solution, would be x of t is equal to a1 exponential lambda 1t plus a2 exponential lambda 2t. Putting for lambda 1 and lambda 2 in our response equation, it would be x of t is equal to exponential minus zeta omega nt, and inside the parentheses we would have a 1 exponential iota omega nt under the root 1 minus zeta square plus a2 exponential minus j omega nt under the root 1 minus zeta square. So if we would look at the equation, here we have an iota function. It is exponential iota function, iota theta. And exponential iota theta, if you remember that, it is actually cos theta plus iota sine theta. So it is an exponential function. It is actually a sinusoidal function. You see cos function there, sine function there. So it means that in this case, this response would be actually a periodic function. It would be a sinusoidal function. But if we look out of the parentheses, there is an exponential decaying function. So it means that the vibration would occur, the vibration would be sinusoidal, but with the passage of time, the vibration would diminish. The amplitude of vibration would decrease with the passage of time, and it would be suddenly gone. We could also write down this response as a exponential minus zeta omega nt sine omega dt plus phi, where omega d is equal to omega n under the root 1 minus zeta square, and it is known as damped natural frequency. So normally in systems we would have two frequencies. One is the undamped natural frequency of the system, and the other would be the damped natural frequency of the system. Omega n is the undamped natural frequency of the system. When we are considering no damping, and we find the natural frequency, which is actually under the root k by n. And omega d would be the damped natural frequency of the system. When there is damping in the system, then the frequency of the system would be omega d. And also you see the phase here. Here we have two arbitrary constants, and in order to find those arbitrary constants, we have to use the initial conditions. Also here, we have two arbitrary constants. One arbitrary constant is a, and the other arbitrary constant is phi. And in order to find these arbitrary constants, we have to use the initial conditions. So using the initial conditions, that is x of 0 is equal to x naught and x dot of 0 is equal to v naught, by putting those initial conditions one by one in the this response equation, then a would be equal to 1 over omega d under the root v naught plus zeta omega n x naught whole square plus x naught omega d whole square, and phi would be tan inverse this quantity. So if you just look at the equation, very easily we could see that the response again would depend upon the initial conditions. So as we just discussed that in this case there would be oscillation, there would be vibration, but as outside the parenthesis there was exponential decaying function, so that means that actually the amplitude of the vibration would decrease slowly and gradually, and after some time the vibration would diminish, it would finish. So in this case, if you disturb the system would vibrate, but with the passage of time the amplitude of vibration would decrease, and after some time the vibration would decay out. So here, if you look here, you would see both of the equations, the simulation of the equations. You would see the sinusoidal function, this is the sinusoidal function, and this is the exponential decaying function. So here, this is the exponential decaying function. This is the exponential decaying function. So the amplitude would reduce by this exponential decaying function. This is the exponential decaying function on the other side. And this quantity, this is actually A. This represents the capital A. So in this case, actually, there would be oscillatory response, gives an oscillating response with exponential decay. Most natural systems vibrate with an underdamped response. So if you disturb the system and it vibrates for some time under free vibration, and the vibration is for some time and then it decays out, it means that in that system is underdamped system. The damping in that system is less than the critical damping.